All right, guys. Way back in chapter 4, one of the questions that was posed was if you happen to have a linear network, uh, and by linear network we mean a circuit that's composed of voltage sources, current sources, and resistors, then what kind of a load can we actually hook up to the linear network so that we can draw the maximum amount of power from the linear network? And the answer was actually answered, right? The value of the load that will result in the maximum power transfer is such that the resistor or the load resistance had to match the Thevenin resistance of the circuit itself. Now, this question is also important when we're dealing with circuits that are undergoing sinusoidal steady state, right? So we want to go back and revisit this question. And one of the things that you will see is that the actual value of the load that will result in maximum power transfer will be related to the Thevenin impedance, but it won't be the exact Thevenin impedance. It will actually be a complex conjugate of it, right? But it's going to take us a little bit of while to get to that result. So here we want to concentrate on the question of maximum power transfer. And let's begin with the diagram. So suppose that we had here some sort of linear network. It has two terminals here, for which we can actually hook up a load. And in general, we actually have some sort of load impedance now, right? It's not just a resistance anymore, right? Now, this linear network that's undergoing sinusoidal steady state, we can actually replace with its Thevenin equivalent. Right? So here, its Thevenin equivalent is going to consist of a Thevenin voltage source and some sort of Thevenin impedance like this, to which we're actually connecting some load impedance. Now, keep in mind that one of the things that's a tacit assumption, right, and it's a tacit assumption about one particular element of this network, it's this Thevenin voltage, right? The Thevenin voltage is assumed to be the effective Thevenin voltage. So here, this Thevenin voltage is the RMS value, or the effective one. Right? Now, we can also say, so this right here is an assumption. So I'm going to box it in red. We can also say that without loss of generality, that the Thevenin impedance can be rewritten as the Thevenin resistance plus J, the Thevenin reactance. Right? It's two parts in general. Similarly, the load impedance can be rewritten as the load resistance plus J, the load reactance. Right? And the question that we want to ask, again, just to make it absolutely clear, is what value must the load impedance have such that the max power is drawn from the network? Now, one thing that we also need to clarify is that we've been talking about multiple types of power. We have the complex power, we have the apparent power, we have the reactive power, we also have the active or real power. Which power are we talking about? Well, we're talking about the power that will actually go into doing useful work. So here, out of all the powers that we'll be focusing in on, that we want to maximize, it is the real power that we want to maximize, right? It's not the apparent power, the complex power, or the reactive power. So it is the real power the ones that we want to maximize. So the active power you need. Now, one thing that we can also do, right, is remember, this is a clarifying set of statements that Z Thevenin, which includes these two parts, and again, this is important to state, this right here is fixed. It is a constant. We have absolutely no control whatsoever about what this Thevenin impedance is. What we do have control over is what this load impedance is. So this right here is not fixed, this is variable, not constant necessarily. Right? So the strategy is going to be to determine this question. Strategy. I know I spelled that wrong. There we go. Is to find an equation for power. So it is defined, which is going to be a function of two parameters. Why? Because we have control over two things here. We have the control over the load resistance, and we also have control over the load reactance. So here we're going to rewrite it as a function of the load resistance, the load reactance, and then we're actually going to maximize this function using calculus. Right? But let's concentrate on the first part. Let's actually find this, and then take the partial derivatives. Set to 0, then solve. But we still need to find now what is this power in terms of these two variables. And the way we're going to do it is the following. Again, we know that from this diagram, if we have a Thevenin voltage, right, that's actually providing us with this voltage, there is going to be a current that flows through the circuit. So there's going to be an effective current that flows through both of these elements. And that effective current, because the Thevenin voltage, the Thevenin impedance and the load impedance, since they're in series, we can definitely say the effective current here, well, it's got to be the effective voltage divided by the series sum of the Thevenin impedance plus the load impedance. This can be further expressed in the following manner. We know that the impedance here and the impedance there, they have a real part and they have a reactive part. So that can actually be rewritten as the Thevenin resistance plus the load resistance plus J, the Thevenin reactance plus the load reactance. Now, I pushed this up a little bit. Let's actually rewrite it down here. So we can definitely say a little bit cleanly that the current that flows through our circuit, well, it's got to be the Thevenin voltage divided by Thevenin resistance plus load resistance plus J, Thevenin reactance plus load reactance. Now, one of the things that we showed previously, and this is we also know from previous calculations, that the actual real power, right, which in general would be the effective voltage times the complex conjugate of the effective current, well, this is the magnitude of the current squared times the load resistance like this. Right? This is something that we calculated previously. Now, we know exactly what the effective current is, so if I can actually find the magnitude of it, then I can plug it into here and we'll realize what we were looking for. We were looking for the power as a function of the load resistance and the load reactance. So here, I'm going to concentrate really on finding the magnitude of this effective current. And I can find it by finding the magnitude of this equation up here. Now, remember that if you take the magnitude of this, well, it's the same thing as taking the magnitude of this. So here I have this. And in fact, we're not just looking for the magnitude of this, we're actually looking for the magnitude of the square. And one of the ways in which I can do it is I can take that phasor, take its complex conjugate, multiply it by itself, and I'll actually get those magnitudes. So here, this right here is the same thing as the effective current times the complex conjugate of the effective current. So here, I can say that I have the effective voltage times the large beast of the impedance, like this, and times the complex conjugate of this, I need to take the complex conjugate of that. Well, it's not so bad, because the complex conjugate of V effective times V effective is just the magnitude of V effective. So here, this is the magnitude of V effective squared. And on the bottom here, it's going to be this term squared plus that term squared. So I can definitely say as well, based on previous calculations, this is actually going to be V Thevenin plus RL Henry squared, because that's the real part, plus the reactive part quantity squared. So we have now just found an equation for the magnitude of the current squared. To find the power, all I have to do is multiply it by the load resistance, in which case I end up finally with the power equation, which is, it's the magnitude of the Thevenin voltage squared, or the effective voltage squared, times the load resistance divided by the Thevenin resistance plus the load resistance quantity squared, plus the Thevenin reactance times the load reactance quantity squared, like this. This is the important equation that we actually wanted to get to. Notice that this is actually a function of the load resistance and the load reactance. This is the equation that we want to take the particles' derivatives of. We're going to set them equal to 0, and then solve to see what consequences that actually has.